stuff. All right, so this is what happens, right? So the hydrogen now donates electrons back to the ring, and the proton itself is getting to react with the bromine in order to create hydrogen bromide and Friedel-Crafts catalyst. Now, I want you guys to bring back to the concept, right? What is a catalyst? Anybody? What is a catalyst?
Anything that speeds up the rate of a chemical reaction
Hmm. All right. And
without it itself going under any
and
chemical changes.
in the
lovely.
reaction.
Without itself going under any type of chemical changes, right? Net chemical changes, because it does undergo chemical changes sometimes, right? So in this case, Friedel-Crafts catalyst is FeBr3. We started with FeBr3, then it became FeBr5, then it became FeBr4, and now it is back to FeBr3. It is remained chemically unchanged at the end of a reaction, and that is exactly what the catalyst should do, right? So it is a perfect catalyst, and really and truly, it's a halogen carrier, right? And it is a Lewis acid. So three different definitions for this type of Friedel-Crafts catalyst, right? That is the bromination of benzene. Okay. All right. So it's the same. It's reacts the same. It's generally the same thing for the nitration of benzene. All right. So let's look at the nitration of benzene. Hopefully it can work. Let me just add this. All right. So the nitration of benzene. So we can see this, right? So after bromination, we look at the nitration of benzene. Benzene is nitrated by concentrated nitric acid, right? Concentrated nitric acid at 55 degrees Celsius in the presence of concentrated sulfuric acid, which acts as a catalyst. This is the condition, and we need to know all of it, right? I want you guys to know everything about it. So we're using nitric acid, all right? In the process, we're going to end up with nitrous acid and hydrogen sulfate and those type of things. Now, the first step that we need to do is show the creation of the nitronium ion, which we use. All right, show the formation of the nitronium ion. This is the formation of the nitronium ion. So when somebody asks you for, what is the mechanism of the nitration of benzene, right? Nitration, all right? Before you start anything, we create our nucleophile or our electrophile. Notice that is exactly what we did in the bromination of benzene. The electrophile was not strong enough, so we used Friedel-Crafts catalyst, creating a complex which acts as the electrophile. So notice in your reaction, you always show the creation of your electrophile or your nucleophile if it isn't already there. So now we do not have nitronium ions in solution. We must create nitronium ions by reacting nitric acid with sulfuric acid, right? We're going to end up with nitrous acid and hydrogen sulfate, and that nitrous acid will decompose, right, in order to provide us with nitronium ions and water. And it is the nitronium ions which go through electrophilic attack of the benzene ring to create nitrobenzene. Any issues? And the hydrogen reacts with the hydrogen sulfate to create sulfuric acid. So the catalyst itself is remained chemically unchanged at the end of the reaction. All right. Any issues? What I'm going to say now is that you guys don't need to see how it happens. You guys don't need to see it. You know why? Because all you need to do is treat nitronium as an electrophile. It occurs in the same way as you see here. All you're going to have now is NO2 doing that, right? So the electrons go to NO2 and then whatever, whatever. It's the same thing, same thing, same thing, same thing. Once you know the bromination of benzene, the mechanisms for all other aromatic compounds are extremely similar. It does not change. All right. So all you're doing now is using with nitro, the nitronium ion. I'm gonna create small clip videos of doing each and every reaction, It's going to be tedious, but I'm going to do it anyways, right? But it's essentially the same thing. Are there any issues with this though? All you do is form the nitronium ion, and then you do the same thing. Electrons go from the ring to the nitronium, right? Creating a nitronium substituent, breaking the stability on the ring. The positive charge will always move around the ring until the hydrogen redonates its electrons in the bond back to the ring to stabilize the ring, and then the hydrogen goes and reforms sulfuric acid. That is what is happening here. That is literally what is happening here. You can see it on the slide. All right. Any issues? Let me write the HSO4 right here. That is wrong. The HSO4, I think it's important to have this. The HSO4 and the hydrogen goes back to the HSO4, right? To reform H2SO4. Lovely. Any issues? All right, seems like everything is good. All right. So let me just check the chat real quick. All right, everything seems fine. Okay, ready to move on?
Oh, what time you said that, sir?
Oh, it is 7. Oh, it's 2 hours. It's 6 to 8. But if you guys want to actually stop at the reactions of benzene, this is actually the last reaction of benzene. Do you guys want to do the rest of it tomorrow?
Sir, it's up to you.
You say it's up to me. Hmm. All right. So
You
you're tired. Crazy stuff. So let me actually get what's happening here. So tomorrow, I guess we'll look at the reactions of methylbenzene. All right. We can do that. Okay. So let me just bring up. I'm gonna send you guys a PowerPoint, right? What you need to know as well, right? So we're gonna go through all of those type of stuff. For tomorrow, we're just gonna look at methylbenzene, name substituents of methylbenzene, then we'll look at the nitration, bromination of methylbenzene, then we'll look at the nitration of nitrobenzene and the bromination of nitrobenzene, as well as the reduction of nitrobenzene. Then we look at the reactions with alkali, for phenols.